How do we train in an unsupervised manner? So there are a few different ways. One popular strategy is to constrain the latent representation while optimizing your score or minimizing the energy function at the training samples. So the idea is that in order to compute the energy function, you need to go through the feature space. And now if you constrain the feature space and you minimize the score at the training samples, by construction, the other input data vectors will have higher energy. Here is an example, k-means. That's the simplest one, where the feature space consists of vectors that are with n entries, and all entries are 0 except for one which is set to 1. And the decoding consists of multiplying this feature vector by a matrix that stores in its columns what you call prototypes, and this matrix is what is subject to learning. So basically, by multiplying with a 1 of n code, you're going to select one column of that matrix, and that is going to be the reconstruction that has to be close to a training sample. And so in this case, we have 3 training samples and 3 features, 3 codes, and each of them maps to a training sample. And there is also the other mapping, which is from image space to feature space. And in the case of k-means, this is an implicit mapping, because what you do, given an input, you're going to find out which code produces the smallest reconstruction to the actual input that you have. And so you have to loop over all possible possibilities, and then you assign the feature vector that yields the lowest reconstruction error. The point is that if you take any other input data vector that is not a training sample, it's going to be associated to a feature that has already been booked to represent a training sample. And so when you reconstruct, it's going to have necessarily much higher reconstruction error, so much higher energy. And therefore, your model is able to discriminate between things that are similar to training samples and things that are not similar to training samples. And by doing so, you're going to discover the intrinsic structure in the data. And I'm pretty sure that you are super familiar with sparse coding. That is just a variation on the theme, where now the feature vector is not just 1 of n, but you relax that constraint. You allow for a few non-zero entries in the code. Another method that falls within this class of approaches is autoencoder neural nets, where you map into a lower dimensional space. And so only a lower dimensional manifold and possibly highly nonlinear manifold of the input can be reconstructed well. There is another strategy, and there are many more actually, that is very popular. And that is the maximum likelihood strategy, where at training time, what you are trying to do is to increase the likelihood of your training samples. But at the same time, you force your model to produce a distribution which is normalized over the input space. So now if you increase the likelihood at some regions of the space, by construction, you're going to decrease it elsewhere, because you want to enforce normalization to 1. And therefore, you satisfy that first principle, which was to give lower energy or higher probability to training samples than other data points. So in today's talk, I'm going to focus on a method that is probabilistic, that uses this second strategy, while tomorrow I'm going to talk about another method that instead uses the first kind of approach. And the outline of the talk is going to be the following. I'm going to start with the mathematical formulation of the model, explain how we train it. And then this afternoon, I'm going to go over a few different applications. And the point of my talk is really to share with you the main motivation and ideas why we came up with this model, and how it also relates to other standard approaches, in probabilistic approaches. So there are a few different ways to compare probabilistic models. You can look at the margin distribution and say, okay, this model makes this assumption, this other model makes this other assumption. So you can look at also other distributions, for instance, the condition distribution over the input given the latent variables. And this is an alternative way of looking at things, and it is usually a bit easier. So if we look at the condition distribution, so call X the input and H your latent variables, then the condition distribution, so for there is a very large class of models for which the condition distribution over the input variables is a Gaussian. Is a Gaussian where the mean depends on the latent variables. It's typically a linear projection from the latent variables. And the covariance is very simple, is either spherical or diagonal. It doesn't depend on latent variables. And if you think about, for instance, probabilistic PCA or factor analysis or independent component analysis or Gaussian RBMs, all make this assumption. And so the idea is that if you look at the toy illustration on the bottom, by the way, the slides are on the IPAM summer school website, so you can download them and follow with me. Now if you generate, for a given feature vector, here, if you generate, you're going to generate from, say, a spherical Gaussian. And what does this mean? So now let's look at this toy illustration. Say that we have an input image, this lady, this Marilyn Monroe here. And let's use the posterior distribution over the latent variables to compute the representation of the model for this image, for this particular image. Now, if we use the condition distribution over the input P of X given H to generate for this given set of latent variables, we may get an image that looks like this. So an image where you have roughly the correct mean intensity, but certainly not the pairwise correlations, the correlations between the pixels, just because the covariance is spherical or diagonal. It doesn't capture the fact that nearby pixels in images tend to be strongly correlated, right? So this is a limitation for this class of approaches. There are other methods that try to cope with this limitation, and one of them is called product of student T. So Russ before mentioned the product of experts model, and this is a product of experts where the experts are student T distributions. And in this class of models, the condition distribution is now a Gaussian that has zero mean, and the covariance that depends on the latent variables. So by every configuration of latent variables determines the covariance function, and therefore a different sets of dependencies between what you observe. And so if we go back to our toy illustration that we had before, now if you generate from the condition distribution of the input given the latent variables, you might get an image like this. So take two pixels here in the forehead, they take pretty much the same values, and they take the same values also here. Take the two pixels in the background here, they take the same value, they take the same value here. So this is an image, this model captures the correlation. So it tells you, it doesn't say anything about what is the actual value, it tells you that this pixel and this pixel take the same value or not, something like that. And so now you also know what was the probabilistic model that Andy Warhol used in his paintings. But of course, if we want to claim that we have a good model of natural images, this is not satisfying because we would like to be able to model both mean intensity and correlation in images. And so this is basically the whole point of this work, where basically we extend these previous models in such a way that the condition distribution is now a Gaussian where both mean and covariance depends on latent variables. And we call these models, so I came up with two variations of these models. One is called mean covariance restricted Boltzmann machine, MCRBM, and the other is mean product of student T, MPOT. And they are basically the same, but differ on the choice of the distribution for the latent variables. And the idea is that now if you generate from the conditional distribution of the input given the latent variables, you get, and if this is the origin of the space, you get a covariant, a Gaussian that is not centered and that has a certain covariance that depend, and both mean and covariance depend on latent variables. And now, in the previous talk, Ross mentioned that you can interpret these models in terms of their marginal distribution as a mixture of Gaussians that have an exponential number of components. And this is yet another example where if you write P of x as the marginal over the latent variables of P of x given h, that for us is a multivariate Gaussian distribution with mean and covariance that depend on latent variables, times a prior over h that actually it's pretty tricky to write down. But this can be thought of as a mixture of Gaussians with many, many components, with an exponential number of them. And so the key idea is that if you want to tile the space or to represent the manifold where the data lives, you are better off describing this manifold with a bunch of Gaussians that have a mean and a covariance that you can adapt, as opposed to a bunch of Gaussians that are all spherical, or a bunch of Gaussians that are all centered at 0. So it is a much more flexible model. And to go back to our illustration, basically before we said that this model would be a good model for the covariance, for the pairwise relationship between pixels, while this one was a good model for the overall mean intensity. And basically what we do, we combine these two models, and so we get the mean intensity as well as the pairwise correlations. And so this could be a sample from, so if you got latent variables here and you generate, you might get a sample that looks like this, that is somewhat closer to what you observe. Now the question is, how do you do this? How do you have a model where both mean and covariance depend on latent variables? And there are many, many ways of doing this, and I'm just going to tell you one way of doing this. It's not necessarily the best way, it is just one way. And it is perhaps the simplest way. So it is the simplest way because it starts from the observation that you can build a multivariate Gaussian distribution with a certain mean and covariance by simply multiplying together Gaussian. So if you multiply together a Gaussian that has 0 mean and full covariance with a Gaussian that has a mean and spherical covariance, you get a Gaussian that has a certain mean and certain covariance. So the geometric interpretation is the following. So we have a model, we do have a model that yields a conditional distribution that has 0 mean and the covariance that depends on some latent variables. And we have another model that produces a Gaussian that has a mean that depends on some other latent variables and has a spherical covariance. Now, if you multiply two Gaussians together, you still get a Gaussian. And you get a Gaussian with a mean that is some sort of interpolation between the two means, and the covariance that is related to this covariance matrix here, has the same eigenvectors. So that's the basic idea. And now I'm gonna go over the details of the model. And so that's my notation. So the input is a vector x. So here I'm really interested in images. So I always think about x as a vectorized image patch. So if I consider 10 by 10 patches, then this is a vector with 100 components. And then I have two sets of latent variables, what I call the covariance latent variables that will control the covariance, and the mean latent variables that will control the mean. And for simplicity here, I assume that these latent variables are binary, but they need not to be binary. You can choose other distributions than Bernoulli. And as usual, my probability density function is going to be a Boltzmann distribution. So it's going to be proportional to the exponential of a negative energy. And so the problem will be to define a suitable energy function. So let's build the energy function incrementally, okay? And we start with a pairwise Gaussian MRF. So where the energy function is a function of the input and the two latent variables, but for now we are not using them, is simply a quadratic, okay? And so this means that you have a Markov random field where the coupling between every pair of pixels is given by the entries of this inverse covariance matrix. Now, I factorize this inverse covariance matrix as an outer product. As an outer product between two matrices, actually a matrix by its transpose. And this matrix C is wider than taller, so that when I take the outer product, I get a full rank matrix. Okay? And so now, because of this factorization, the graphical model can be drawn as a factor graph, because, okay, so it's a pairwise Markov random field, because if you take this quadratic form and you expand, you get all pairwise products between the input variables. That's why, and with alphas that depend on the entries of matrix C. But you can write it also as a sum over F factors, where the factors are actually the filter responses. So you can interpret that each column of matrix C is a filter that you apply to the image. And now each filter output will give a contribution to your overall energy function. And so this can be drawn as a factor graph where you have F factors. You have an energy function that is a sum of F terms. And basically, you're going to multiply the input by a matrix C here. But because you have also a matrix C here, you take the square there. And so you multiply two things, and that gives you a term to your energy function. And the idea is that you would like your energy function to be small or lower at the training samples. And so you can see that a way to, so when the input matches your filters, actually the energy increases. So that's something that we will come back later. It is something interesting to notice though. So now we don't have latent variables yet. So we want to introduce latent variables because we want our covariance matrix to depend on latent variables. And a simple way to do this is to introduce a diagonal matrix between the C and the C transpose. So now imagine that the first entry in vector HC is very, very small. So that means that you're going to downweight a rank 1 matrix that you add to the inverse covariance matrix. That is the first filter times its transpose, which means that the overall covariance matrix is going to, so the Gaussian is going to stretch along the direction of that filter. So by changing the configuration of the latent variables, we are going to stretch the covariance matrix in different directions. And the graphical model now becomes like this. We have also these latent variables. And the factor now is not a factor between two things, it's a factor between three things. Okay? So the three things are the latent variables, and the filter response is here, and the filter response is there. And so you still have the F terms in the energy function, but now each term is weighted by these latent variables. And we can further extend the model by introducing matrix P, a matrix P that is going to be here, that basically takes a linear combination of latent variables. So now you have a sum of F terms And each term is going to be a linear combination of latent variables and the square filter outputs. And finally, the last addition to the model is the mean part. So the mean part is very much a Gaussian restricted Boltzmann machine. So basically, you have a quadratic term and then the usual RBM term, where you couple the input pixels to the latent variables. And in terms of the graphical model, it's going to be like this in the case where you have 2 pixels. And so this goes back to our previous geometrical interpretation, because now if you assume that you know the state of the latent variables, the HM and HC, then this on the top is a quadratic. And you sum 2 quadratic terms. One that corresponds to a Gaussian that is centered at 0, that's this thing, and one that is spherical with a non-zero mean, that's that one. And now, if you think about what's going to be the condition distribution over your pixels given the latent variables, it's going to be a Gaussian that has a non-zero mean and a full covariance. And that's exactly what's written here. So this energy function defines an inverse covariance matrix that is equal to this quantity plus the identity that comes from the mean part. And then the condition distribution is going to be a Gaussian that has this mean and that covariance, okay? So it's very simple. Now, there is a tricky part. So if you compare this with a Gaussian RBM or with a standard restricted Boltzmann machine, you realize that the computation involved in computing a sample from this condition distribution is much more expensive. It is much more expensive because the model is defined in terms of an inverse covariance matrix, not in terms of a covariance matrix. So you need to do some matrix inversion. You need to do some scholastic decomposition in order to draw samples from this multivariate Gaussian distribution. And now the matrix inversion is basically is an iterative process, and you can think of it as solving a linear system. So you do via variable elimination. So it's an iterative process. And this is the iterative process that you have to deal with when you have a pairwise Markov random field, and you need to figure out the state of the variables in your Markov random field. Because given the latent variables, that what we describe here is a pairwise Markov random field. And so we need to do some iterative procedure. Or in other words, you need to do a matrix inversion, which is a bit expensive in order to sample from it. So that's an example of a more sophisticated RBM, where you have interactions between the variables, where the variables, given a set of variables, the other variables are not independent in this case. And however, computing the latent variables given the pixels is very easy. It's still very easy because there are no links between the latent variables, neither here nor here. And in fact, computing, let's start from here, computing the probability of a mean latent variable taking the state equal to 1 given the input is like the standard computation that you do in a RBM. You just do a weighted sum, add the bias, go through a logistic that gives you the probability. For the covariance latent variables, it is a bit more interesting because now all you need to do is do a weighted sum, apply your filter bank to the input, then square the filter outputs, linearly combine them, and then you go through a nonlinearity. And this is reminiscent of the very standard, simple, complex cell models of early visual areas in V1, where you have a complex cell that is just a rectified version of a linear filter bank. So here the rectification would be the square. And you can see that here, because you square and because you take a linear combination, that there are many inputs that can be mapped to the same output. So there are many x's that yield the same total sum here. So you have a bit of invariance, and we will see that also later when I'll talk about the experiments. So let me step back a little bit and reinterpret this model from a different perspective. Before I go on, is there any question on what I have described so far? Is everything clear? All right. So, yes?
So why did you introduce the P?
Why introduce the P? So, an idea is that you would like the latent variable. So, okay, let's see. Oh, sorry. This latent variable here is gonna not take, so if P is identity, then it's like the other model, the basic model, right? But now, by allowing P to not to be identity and to be something else, you're gonna make this feature, this latent variable, depend on many filter outputs. And so basically, you have a whole subspace of the input that is gonna map to the same feature. And now, one key problem in vision is invariance. So you would like to be able to map many inputs into the same output. Many inputs that are irrelevant for your classification task, say different pose, slightly distorted inputs into the same feature. And the matrix P achieves that. Because basically, it may become clear when I show what actually the C and the P are. But basically, you are, for instance, mapping. So C can be a Gabor function. You may learn something that looks like an edge detector, and the P is going to group similar edges in similar orientations, basically. And so basically, that latent variable then is going to respond no matter what is the precise location of the edge. So P is good for improving the invariance properties of the model. So let's look at another interpretation. Now, let's assume that we have only one filter, and that the energy function is this one. Now, if we want to minimize the energy function over our training set, subject to a constraint on the normal W, then what we would discover is the minor component. So W will converge to the principal component with the smallest eigenvalue. The reason is that what you want to do here is minimizing the average variance. Principal component analysis finds the projections that maximize the average variance, while here we want to minimize that. And so in the case of natural images, you would learn a W that is very high frequency, like a checkerboard, a gradient. So in the case of 2 pixel images, then the W would be something like -1 + 1. And that's because images tend to be very smooth. And so what's very common in images is to have low frequency, smooth images. And here we are looking for things that are very rare, very infrequent, right? That almost never occur. And this edge in the Markov random field is nothing but expressing the strong dependencies between nearby pixels. It says that nearby pixels have to usually take pretty much the same value. And another way of saying this is that this energy function is expressing a constraint. So it says that most of the times pixel takes the same value, okay? Because if you give an image, an X that is not smooth, then the energy is going to become large. It's going to take a large value. And so that's going to have low probability. So this model is basically detecting constraint violations, okay? Or is enforcing constraints that are most of the times they are satisfied, in other words. So, but if you think about what we would like really to do is to be able to, yes, have a model that says that images should be smooth, but at the same time, to be able to represent also, say, edges, which is basically the structure that is in images, right? So the role of the latent variables is to capture the violations of these constraints. And basically, if you multiply this square filter output by the latent variable, and you add also a bias that is positive, and you multiply that by the latent variable, if the latent variable is binary, the latent variable acts like a switch. So when the image is smooth, then W transpose X is going to be equal to 0, because W is a very high frequency thing that comes from the minor component. You multiply by something that is smooth, and you get 0, right? And in this case, if the latent variable is equal to 1, you get an energy value that is equal to the minus bias, which is a negative value, okay? And the Markov random field, when this is equal to 1, reduces to this, okay, for a 2-pixel image. When the image is not smooth, that is the case when you have an edge, for instance, then if you set the latent variable to 0, then, so if the image is not smooth, you can see that this term is going to be very, very large, because W transpose X is going to be very large, right? Because the input matches the filter. And the latent variable allows you to discount, not to pay a very large penalty in terms of square filter output. And by setting the latent variable to 0, you get an so if this is multiplied by 0, multiplied by 0, you get an energy which is 0. So you got a big discount in terms of energy. You don't pay W transpose X squared, but you pay 0. So introducing the latent variable allows you to model breakdown of smoothness or violations of constraints. And this goes back to the fact that if you compute the energy corresponding to the marginal distribution of the input, so if you look at the marginal distribution is going to be something proportional to exponential of a negative energy. And this can be computed exactly by marginalizing out the latent variables. And that's the computation that is given here. And if you plot this energy function as a function of the filter output, you find that this energy function is not a quadratic. It's a function that looks like this. Basically, it discounts large violations of the constraint. So it discounts when this W transpose X is very large, you don't pay as much as you would if it was quadratic. And this is known in statistics as robust statistics. Whenever you want to be robust to outliers, you replace your square Euclidean distance with something that looks like log student t. And that's an instance of this thing. And this goes back to the line process of the early 90s, if you know that literature, and to the robust statistics. The other interpretation of the gated MRF is in terms of a Markov random field where the couplings are input dependent, in the sense they depend on the latent variables. And you can think of it as if you have a model where the parameters are actually a function of some other variables, in this case latent variables. And this connects a little bit with Bayesian nonparametrics, where the number of parameters scales with the number of samples that you have. Also here, because of this gating, it's a very powerful model because the actual number of parameters is very, very large. For every input, you get a different set of parameters, basically. So the take-home message is that we have a Markov random field that has latent variables, and one set of latent variables is just taking care of setting the biases for what you see here, for the visibles. Another set of latent variables is instead modulating the couplings between the latent variables. So now let's look at a simple demo to show what each latent variable is doing for a practical case. So this is after training on natural image patches. So this is an image patch that the model has never seen before. And if you recall the condition distribution over the input, is a Gaussian that is the product of two terms. One comes from the covariance latent variables and the other from the mean latent variables. And so now on the top here, I'm just showing each of these two terms. So the reconstruction coming from the mean latent variables is shown here. And the overall reconstruction, the multiplication of this covariance matrix that depends on the covariance latent variables by the reconstruction from the mean latent variables is shown here. So you can see that the reconstruction from the mean latent variables looks very blobby, right? It's very faint, very blob. But when you combine this information with the one coming from the covariance latent variables, you get a fairly good reconstruction. Why is that, right? So one thing that I did was to cheat. And basically, instead of using the reconstruction from the mean latent variables, I set it by hand, okay? And I set the reconstruction to all 0, except for one spot, one small blob. And I say that this blob has to be negative, it's darker, right? Now, if you multiply this thing by the reconstruction coming from the covariance latent variables, you find that the reconstructed image is now a smear blob, because the covariance latent variables know nothing about the mean intensity of the pixels, but they do know that which pixels have to take the same value. And so basically, it is trying to interpolate between this pixel and this pixel or in this region, because it knows that pixels in this area have to take pretty much the same value. And that's why the mean latent variable can be very sloppy at representing and reconstructing, because basically, if you specify just in a few places what the deviation from 0, you can already get a pretty good reconstruction, because in this case, it knows that all pixels here in this area have to take the same value. And if you tell it that it has to be bright, then it makes everything bright. And this will set all this region to dark, as you can see here. And the covariance latent variables know nothing about the mean intensity, and therefore, if you flip now the sign of the mean reconstruction, you flip the sign also of the overall reconstruction, right? So I think that's a pretty cute demonstration of how these latent variables conspire to reconstruct the input. Let me give the big picture now. So if you have a bunch of data points, say these blue dots, principal component analysis will basically compute one mean and one covariance for all data points. And now if you give me a new data point, which is the red dot, it's going to try to reconstruct it as a point in the principal components. It's a projection, right? A probabilistic extension, PCA, is probabilistic PCA, where basically the condition distribution is going to be a Gaussian. And so the mean is, again, very much like in PCA, is a projection on the principal components. And the covariance is spherical, okay? Factor analysis is an extension of PPCA, where the covariance matrix is actually diagonal. And you learn the diagonal variances, but they are not dependent on latent variables. In sparse coding, the condition distribution is, again, spherical, but now the way that you set the mean is much more flexible, because you have a much larger set of basis functions to choose from, and you choose very few of them to produce, to tell where the mean has to lie, in which subspace. Then we have seen that product of student T was another model where instead the mean of the Gaussian distribution will be set to the origin of the space. In this case, we center where the data is, and the covariance is set by the latent variables. And in the model that I just described, this mean product of student T, or MCRVM, the covariance now, both mean and covariance depend on latent variables. So it is, in this sense, more expressive. And so all this model, so this model can be seen from many different perspectives, which I think is one of the most interesting things. And it can be seen from related to PCA factor analysis product student T, if we look at the conditional distribution over the input, it can be seen as a third order Boltzmann machine because you have an energy function where you have product of triplets, 2 pixels and 1 latent variable, and that links to the work on third order Boltzmann machines that Roland Memisevich is going to talk about later this week, and the work that also Graham has been working on. But in their case, they would take 2 frames, 2 consecutive frames from a video, and they would try to relate how pixel I in the first frame relate to pixel J in the second frame. While in my case, the 2 frames are the same image. So I'm looking at dependencies between pixels within the same image. And then this model also relates to the line process. If you interpret the latent variables as switches, if the switch is on, you have strong dependencies between the pixels. If it is off, you break down those dependencies. It is also related to standard models in computational neuroscience for the simple complex cells, if you look at the posterior distribution over the latent variables. So let me conclude with how we train this model. So the parameters that we want to train are those highlighted here. We have the filter bank C that you use to project your input, then the matrix P that linearly combines latent variables, and then you have the matrix W that yields the reconstruction from the mean latent variables, and then you have also a set of biases. What you can write is the marginal distribution P of x as some integral over the latent variables of the exponential of the negative energy function shown here. It turns out that you can compute this integral on the top, and basically that's the energy function f that we have seen before. This energy function f is the negative log of the integral over the latent variables. Doing the math is actually a very nice homework. If you have never done it, I recommend it to you. It's really fun. I'm serious. And it turns out, so it goes back to the previous slide where you basically enumerate over possible latent variables, and then you get an energy function that looks like this. So it's very simple and it's instructive. And so basically, once you have your energy function f, you define the negative log likelihood. And then if we want to maximize the likelihood, we want to compute the gradient and update the parameters by standard stochastic gradient descent. Computing the derivatives, now we link back to what Russ has described earlier. All you need to do is computing the derivative of the energy function with respect to the parameters. And you compute that for an x that is drawn from the training set and from an x that is drawn from the model distribution. And that's the tricky part, how you draw samples from the model distribution. And in order to do this, we use an MCMC method. So I'm going to give you a very quick overview of how this works, and more details will be given later this week by Yain when he will talk about MCMC methods. So the idea is the following, that you are given a training sample, and this is your energy function. Let's assume that everything is 1D, okay? So you have a one-dimensional input, so I can draw it. And on the y-axis, you have the energy. We start a hybrid Monte Carlo dynamics, which means that let's assume that this data point is actually a ball rolling on this energy surface. And this ball is subject to 2 kinds of energy. There is a kinetic energy because we start the dynamic by giving a random kick, a kick in a random direction with a random velocity. And this ball is also subject to a potential energy that depends on on the value of the energy f at this data point. Okay. Now, as the ball moves, there is no friction, so the sum of these 2 energies is constant. And by using that, we run this simulation. And so you run the simulation. Of course, we need to discretize, but we run the simulation for a certain amount of time, and then we stop. Now, if we stop and we give another random kick and keep repeating this process, eventually we are guaranteed that we sample from the equilibrium distribution. But what we do, because we are lazy, we stop after one step. We stop after one step, and that's the contrastive divergence learning rule or approximation. And we compute the derivative of the energy function at this data point that we just found. And then we update the parameters by taking the difference between these two gradients. And so the effect is that we are going to decrease the energy at the training sample and increase it at the data point that our model thought it was a good sample. And by doing so many, many times, eventually the training samples will be at the minima of the energy function, and eventually these two gradients will cancel out, and you're done with training. Okay? There are many variations of this algorithm, and another variation is to, instead of resetting, starting the dynamics from the training sample, you let these particles run. You never bring them back to the training sample. And basically, if the learning rate is small compared to the mixing rate of the chain, eventually the approximation gets very good because you sample from the equilibrium distribution with good approximation. So that's how we train it, and I will stop here and take your questions if you have any. Thank you.